right? Identifying what an ionic compound is. We've looked at the bonding model, right? We've now used the model to list and explain the properties of ionic compounds. And now we're going to look at naming and balancing ionic compounds, right? So students can find this challenging. That's what the first two worksheets in that worksheet pack are about. So our success criteria says state the formula of ionic compounds formed from monoatomic ions of the main group elements 1 to 13, 15 to 17. So notice we don't have 18. Why don't we have 18 in there? What do we know about group 18? They have a full valence shell. They're non-reactive. What about 14? Why is 14 not in there? How many valence electrons are in group 14? Well, how many are there? 4. How many do we want? We want 8. Is it easier to lose 4 or gain 4? It's about the same, right? So we're going to look at group 14 later because they have a tendency to share, which goes into covalent bonding, which we'll get to. So monatomic, mono meaning one, atomic, obviously atom, and ion, meaning charged particle. So our main group elements, right, the charge is fairly straightforward. All group 1 ions will have a 1 plus charge. All group 2 ions will have a 2 plus charge. Notice the formatting is that the value of the charge goes first, followed by whether it's positive or negative. All group 13 ions will usually have a 3 plus charge. So for example, aluminium, 3 plus. Any questions on that? Okay, so moving on to group 17. Group 17 wants 1 electron to complete its outer shell. So it's got 7, it wants 1 more. Electrons are negatively charged. So if I've got 1 more negative, I'm a -1 or a 1 minus charge. Does that make sense? What I want you to notice too is how the name changes. Fluorine changes to fluoride. Chlorine turns to chloride. Bromine, bromide. Iodine, iodide. Whereas with our metals, I'll just go back here, our group 1, group 2 metals, the name of the metal remains. So we've got the sodium atom versus a sodium ion. Potassium atom versus potassium ion. The name doesn't change. So a name changes for our non-metals. All group 16, 6 valence electrons, wants 2 more to fill its octet. It'll have a 2 minus charge. Similarly, the name changes the same way. Oxygen goes to oxide. Sulfur, sulfide. Selenium, selenide. This is non-metals. So metals retain their name. Magnesium ion, aluminium ion. Non-metals change to ide. There's an interesting blog called Things I Will Not Work With. And he talks about selenides. And he describes selenide compounds as if it were 6 skunks in an inner tube set on fire. Right? And that's the idea of how much stench that selenide compounds have. When we think about sulfur, sulfur's smelly. Right? So hydrogen sulfide is the reason why farts smell. Whereas, do you know that loud farts don't smell? Loud farts contain greater quantities of nitrogen, which causes the explosive sound that you hear. Right? Silent farts are deadly because they have less nitrogen and more hydrogen sulfide. They stink. Anyway, the chemistry of farts for you. Group 15 ions, 5 valence electrons. Wants 3 more. 3 lots of more minus charge forms a 3 minus charge. Nitride. Phosphide. That makes sense? Yeah? We've got selected transition metal cations. What I want you to notice is with transition metals we need to state what charge it will be, right? Because they can have varying states. Right? They don't just use their outer shell, they can actually use the second to last shell for bonding. So the main ones we're going to look at is iron, nickel, copper, zinc and silver. So iron can have a 2+ or a 3+ charge as the ion. So we use Roman numerals to display that. Iron 2 or iron 3. Nickel pretty much only has 2. Got a little star there. It has been known to have others, but in most circumstances it will have 2. Copper's got 2 different states, copper 1 and copper 2. Zinc and silver only have 1 oxidation state that we know of, or charge. And so zinc is 2+, silver's 1+. Given that it only has 1, we don't have to specify for those the Roman numerals, whereas we do for the others. Are there any questions about that? Hydrogen's a unique case. Yeah, hydrogen's special, helium's a bit special, carbon's a bit special. Hydrogen sort of, when we look at our periodic table, sits just above group 1 because it's got 1 electron. But what do we know about the first shell? How many electrons can we fit in our first shell? 2, right. So it's sort of a group 1 in that it's got 1 electron, but it's sort of a group 4 in that its shell is half complete. So we can either give 1 away or we can take 1. Most circumstances, it will give 1. Right? And we call it the hydrogen ion because once we lose the electron, we only have the nucleus remaining. That's it. It's tiny. So it's the hydrogen ion, also called just a proton because that's what it is, or hydride. Hydrides are only really occur when hydrogen reacts with reactive metals, now group 1 and group 2 metals, because they give off their electrons more readily than hydrogen gives off its. So hydrogen will accept the electron from, say, lithium or sodium. Any questions there? So now let's think about formula. So ionic compounds are neutral. So the total number of ions in the formula must balance, right, so that the overall charge is 0. Or the total charge of all the cations will balance out the total charge in the anions. So when charges are equal in value but opposite, there's a 1-to-1 ratio. So if we take, say, sodium and chlorine, sodium ion and the chloride ion, we've got a 1+ and a 1- charge. Add them together, you get 0. So it's 1-to-1. NaCl, we get sodium chloride. Magnesium oxide. We have a 2+ in the magnesium, we have a 2- in the oxide, 1-to-1 or 2-to-2, they balance each other out. Formula just becomes MgO, or magnesium oxide. If we have a 3+ charge, balancing with a 3 minus charge from something like nitride, we get aluminium nitride, 1 to 1. Yeah? So when the charges are equal but opposite, it's a 1 to 1 in our formula. Any questions there? Pause. What happens when we don't have equal charges? What we do is that we want to balance the charges accordingly. So I call it the crisscross method. We don't have to think of it that way, but I find it fairly straightforward. So if I've got aluminium 3 plus, oxygen 2 minus, or oxide, I want to balance that out. So the easiest way is, what's 3 times 2? Right, so lowest common denominator. Yeah, if we want to think about it in terms of fractions. So 2 lots of 3 gives me plus 6. 3 lots of 2 minus gives me minus 6. Plus 6 minus 6 gives me my 0. So what this means is I'm going to have 2 lots of aluminium and 3 lots of oxygen. Notice the location of where it appears. So we've got our element symbol, and then subscript on the right-hand side tells us how many of those, or really it tells us the ratio of it. So aluminium oxide becomes Al2O3. So here's some other examples. Sodium oxide. Sodium's 1 plus, oxide's 2 minus, so therefore I would need 2 lots of the sodium to balance out the 2 minus charge. It becomes Na2O. Magnesium phosphide. I've got 2 plus from the magnesium, 3 minus from the phosphide. So I'm going to need 3 lots of the magnesium and 2 lots of the phosphide. Aluminium chloride, calcium fluoride, there are plenty of other examples there. Any thoughts on that? Make sense? All right, now it gets a little bit tricky. We have what's called polyatomic ions. The prefix poly means many. So many atoms joined together in an ion. So they're actually covalently bonded within the ion itself, and then ionic bonding with other substances. Here's some common polyatomic ions. Again, pay close attention to the notation, right? I don't care as much for spelling or grammar in chemistry. What I care about more so is notation and formatting. So phosphate, 1 phosphorus atom, 4 oxygen atoms, has a 3 minus charge overall. So I'm paying close attention to where the superscripts and the subscripts occur. So superscript is for the charge, subscript tells me how many of the atoms I have. Sulfate, carbonate, and dichromate, all 2 minus charges. Notice the name, 8, comes from like saturate, meaning the maximum number of oxygens possible. 1 minus charges, nitrates, hydrogen carbonate, hydroxide, or permanganate, and then a 1 plus charge in ammonium, not to be confused with ammonia, which is NH3. All right, 2 more slides and then I'll finish. Formulas. Again, we can have a 1-to-1 relationship. That's nice and straightforward. Ammonium nitrate, NH4, NO3. I can just combine them together nicely. Magnesium sulfate, 2 plus and a 2 minus. Join them together, okay? When I require to balance out where they're not the same, crisscross again, but I group the polyatomic ion in brackets and then put a subscript, as in that example, aluminium sulfate.